All right, so now we'll cover part 2 of chapter 4, which talks about air. So an air parcel is a body of air that has specific temperature and humidity characteristics compared to the air around it. So an air parcel is like a column or body of air that has specific temperature and humidity characteristics compared to the air around it. So a warmer air parcel will have a lower relative density of those air molecules, whereas a colder air parcel will have a higher relative density. And that makes sense when you think about adding energy to air. As you add energy, those molecules will get excited, and as they get excited, they tend to break their bonds to each other increasingly. So the hotter air, the molecules will be further apart, which gives them a lower density. And if the air is colder, the molecules have to be closer together, and that gives them a higher relative density. So within an air parcel, we have two opposing forces that pull the air molecules up and down. So first we have gravity, which of course pulls on everything, and gravity tries to hold these air parcels down and pull them to the surface, whereas the force that fights gravity and tries to pull the air molecules up into the sky is called the upward buoyant force. So air molecules naturally try and move all over the place, and they're trying to rise up into the sky. But for the most part, gravity wins that battle, and it keeps them from moving very far from the Earth's surface. So the majority of the air molecules in our atmosphere exist very close to the Earth's surface because gravity overwhelmingly wins this battle. But on occasion, the buoyancy force will overpower gravity, and that's when the air can start behaving in interesting and sometimes violent ways, as we'll discuss in the next unit. So now we'll talk about the adiabatic cooling process. So as air parcels rise, they expand. The molecules get further apart from each other. And as the air parcel expands, it cools down. The air temperature is lowered. So the adiabatic cooling process just refers to as air parcels rise, they expand, and as they expand, they cool down. So the opposite of adiabatic cooling is called adiabatic warming. And that's when an air parcel warms up as it sinks and compresses. So as the air parcel moves down vertically towards the surface, the air will compress and the temperature warms up. So it's the inverse of the adiabatic cooling process. So adiabatic temperature change simply refers to how the temperature of an air parcel changes as it moves vertically through the atmosphere. Remember, as it moves up, it expands and cools down, and as the air parcel moves down towards the surface, it compresses and warms up. And it does this at the rate of 10 degrees Celsius per 1,000 meters of altitude in an unsaturated air parcel. So again, what we just talked about, that is the dry adiabatic rate that refers only to unsaturated air that hasn't reached the dew point yet. So again, that dry adiabatic rate is 10 degrees Celsius per 1,000 meters of altitude. So if it goes up at this dry adiabatic rate, the air will cool down by 10 degrees Celsius per 1,000 meters. And the opposite is also true, that if the air moves down and warms up, it'll warm up at this rate of 10 degrees Celsius per 1,000 meters, as long as we're talking about a dry air parcel that hasn't reached the saturation point yet. So now we'll discuss what happens when the air rises and cools to the dew point temperature. The altitude at which it does that is called the lifting condensation level, the LCL for short. So the lifting condensation level is the altitude at which an air parcel becomes saturated. It's reached its dew point, and from that point upward, we're now talking about a saturated air parcel. And for the example problems that we're going to give you on your exam, we're going to keep the LCO at a very simple mark that's easy to do calculations with, like say 2,000 meters, 3,000 meters. It'll be something really easy to do the math with. So that's where air has risen and cooled to the dew point, and above this altitude, the process of condensation starts to release latent heat, and that slows down the cooling process. So now from this point forward, we have to use a new rate to calculate this change. This new rate is called the moist adiabatic rate. And the new rate is only 6 degrees Celsius per 1,000 meters. That's both for cooling down and for warming up. If we're talking about a saturated air parcel, the rate of change is 6 degrees Celsius per 1,000 meters, whereas the dry rate is 10 degrees Celsius per 1,000 meters. And it's not necessarily that exact mark at everywhere in the air parcel. That's just a good, easy average that we've discovered over many years of observing this, and it makes for some easy calculations. So in a separate video, I'm going to post some example problems where we'll go over that in details. That'll prepare you for your exam. So the moist adiabatic rate is always going to be less than the dry adiabatic rate, because remember, once it reaches that dew point, the water starts to condense itself, and that release of latent heat will slow down the cooling process. So the moist adiabatic rate will always be less than the dry adiabatic rate. So next we'll talk about the environmental lapse rate. So the previous things we've talked about refer to the temperature change within an air parcel. The environmental lapse rate refers to the temperature change that happens outside of the specific air parcel that we're talking about. So the environmental lapse rate is the decrease in air temperature outside of the air parcel as altitude increases. And the average environmental lapse rate that we use for our calculations is 6.5 degrees Celsius per 1,000 meters. 6.5 degrees Celsius per 1,000 meters. And again, this is a general average and refers only to the air outside of the air parcel, not inside. For the air inside the parcel, we use the moist adiabatic rate, which is 6 degrees Celsius per 1,000 meters, and the dry adiabatic rate if it's unsaturated, which is 10 degrees Celsius per 1,000 meters. All right, so now we'll talk about how the state of an air parcel affects what we see in the atmosphere. So in a stable atmospheric condition, that means the air parcels are cooler and more dense than the surrounding air, and so they can't rise unless they're forced to do so by something else, like a front coming through. So a stable atmosphere is what we see on a normal day. It's very clear, blue skies, not much cloud cover at all. That's a stable atmosphere, which means the air parcels are cooler and more dense than the surrounding air, so they can't rise. In an unstable atmosphere, the air parcels are rising on their own because they're warmer and less dense than the surrounding air. And unstable atmospheric conditions lead to the formation of clouds and some bad weather. The more extreme the difference is between the air parcel and the surrounding air, the more crazy and unstable things can get. And we'll talk about that, especially when we talk about tornadoes in the next unit. That's an extreme example, but generally unstable weather happens in this type of environment when the air is warmer and less dense than the surrounding air, so it starts to rise on its own. And we also have what we call conditionally unstable air parcels. That means the air is unstable until it reaches that lifting condensation level, and then it starts to cool down at a rate that is colder than the surrounding air, so it stops rising in such a violent way. That's called a conditionally unstable air parcel. Air parcels will also go through this heating and cooling process when they run into a physical landform such as a mountain range. So let's imagine the Rocky Mountains, for example. If a parcel of air moves and meets the windward side of a mountain range, the mountains force that air to rise upward and cool adiabatically. And what happens is they cool so much that they condense and they release all of that precipitation on only one side of the mountain. And by the time that air gets to the other side of the mountain, it it goes down and it warms up adiabatically, but it's already released all of its moisture on the other side. So there's no moisture remaining for it to release on the leeward side of the mountain, and that creates what we call a rain shadow. Hawaii is a very extreme example of this because one side of the mountain gets some of the highest precipitation rates on the planet, and the other side is basically a desert because it gets no moisture at all. That's the rain shadow effect. There are four ways which air can be lifted. First, there's what we just talked about, which is convective uplift. That's when an air parcel rises because it's warmer and less dense than the surrounding air. So it convects, it goes through convective uplift. A second example is called orographic uplift, and that refers to when air hits a mountain range and rises because of that. It can't phase through the mountain, it's forced to rise and cool down. And then it sinks and heats up on the other side of the mountain, like the Rocky Mountain example we just talked about. So convective uplift, orographic uplift. Now the third way air can lift is called frontal uplift. And that's when a mass of warm air rises when it hits a cold air mass. Because the colder, more dense air will always force the warmer, less dense air to rise. They can't phase through each other. The cold front is always going to bully the warm front out of the way. And in an extreme case, that could lead to things like tornadoes spawning. When a really cold mass of air hits a really warm mass of air, the warm air will rise very quickly, and that can lead to all kinds of unstable atmospheric conditions that spawn all kinds of bad weather. And the final way air can lift is called convergent uplift. That's the rising of air as the result of converging airflow. And we mainly talk about that in terms of the ITZZ, which I'll cover in the next part. So now we'll talk about the ITCZ, which is shorthand for the Intertropical Convergence Zone. So intertropical simply means between the tropics, because this area will always take place between the boundaries of the tropics or just barely outside of them in some cases. So the ITCZ is the most geographically widespread area of convergent uplift on Earth. The Intertropical Convergence Zone. So it's like a very long boundary that extends all the way around the Earth's surface at a specific latitude. It always follows the subsolar point. So remember in Unit 1 we talked about the subsolar point, which is the latitude on Earth where the sun's most direct energy is concentrated. It'll always be between the two tropics as it bounces back and forth throughout the year. Well, this convergence zone follows that subsolar point because the energy is so hot there, it creates a worldwide sort of low pressure zone everywhere where that area exists. It's going to be very hot relative to the surrounding air, and it's going to cause a lot of air to converge around that latitude. And it tends to create very strong uplift and very violent thunderstorms. And that's part of why we get such bad weather here during the summer in Louisiana, because in July and June, that's when the ITCZ is closest to us. So it draws a lot of frontal uplift to it, and because we're by the Gulf of Mexico, which has a lot of warm water in plentiful supply, it tends to create a lot of nasty thunderstorms in the Gulf of Mexico during that time of the year where the ITCZ is there. And it's also why the monsoons in India happen during the summer there, and we'll talk about that in a little bit. So again, the location of the ITCZ is always dependent on where the subsolar point is. So here in the northern hemisphere, it's closest to us during the summer, and it's furthest from us during the winter. Right now, we're in late March, so we just had the spring equinox. So right now, the ITCZ is just barely across the equator in the northern hemisphere. It would have just crossed it a couple days ago. All right, so we've covered air. Now we're going to talk about clouds. Clouds are composed of suspended microscopic liquid cloud droplets and ice crystals. So the reason they appear to us to be almost very light and feathery or like cotton candy is because they're made up of very, very tiny particles that are bonded together. Some of them are frozen in the form of ice crystals. Others are just very, very cold water that haven't quite frozen yet, but they're very close. And these things are suspended to aerosols. So the reason they bond together is because they bond to things like dirt or pollutants in the atmosphere, and that allows them to bond together in the form of clouds. So clouds are an example of aerosols that we talked about in the first unit. So for our purposes in this class, all clouds take one of three basic forms. So the one that we're most familiar with is called a cumulus cloud. They're dome-shaped, kind of bunched up clouds with a flat base and billowy shapes in the upper part of the cloud. That's what we tend to see most here in Louisiana. They're relatively close to the surface, whereas what we don't see quite as much are cirrus clouds. Cirrus clouds are very high in the atmosphere, and they have a very light, feathery appearance. They're composed mostly of ice crystals. And if you've ever been on an airplane, the cirrus clouds are the last cloud layer that you fly through as your plane breaks into the atmosphere. The last little bit of clouds that you see are you flying through cirrus clouds. Now, the special type of cloud that produces lots of nasty weather is called a cumulonimbus cloud. These are very tall clouds that extend high into the atmosphere in sort of an anvil shape. And these are capable of very strong vertical development and very severe weather. These are the type of clouds that tornadoes spawn from, for example. We'll talk about that in the next unit. I'll show you some pictures of each cloud type from the textbook. So I just realized I misspoke earlier. I told y'all that most of the clouds we see are cumulus clouds. That's incorrect. It's actually stratus clouds. So stratus clouds are the low, flat sheets of clouds that we tend to see on an overcast day when the sky is very gray. These stay pretty low to the surface, and they form in low, flat sheets. So most of the clouds we see on an overcast day are these stratus clouds, whereas on a day with more blue skies, you might see more cumulus clouds because the sky is less overcast in general, but there are still some clouds higher up in the atmosphere that tend to be these cumulus types of clouds. So now I'll show you the pictures from the textbook. So these are the pictures found on page 116 of your textbook that show the different cloud types. So first, we have our flat stratus clouds right here. They form very flat sheets and stay low to the ground. Over here, we have the cumulus clouds that you might see on a blue sky day. They tend to not have too many of these in the sky, but where they do exist, you see them very easily because they're quite big and tall. And then finally, we have the scary clouds, the cumulonimbus clouds, which you see are very, very tall. They're very unstable, so there's a lot of rising of the air within this cloud, and this leads to really nasty things like hail, sometimes really nasty forms of sleet, and of course tornadoes can spawn from these clouds in the right circumstances. So now we'll talk about fog. So fog is not the same thing as a cloud, but it certainly does have a very cloud-like appearance here on the surface. So fog forms when the air at Earth's surface has cooled to the dew point, and that tends to only happen either very late at night or very early in the morning, like maybe on your commute to LSU. You might have to drive through some fog. It's very rare that the dew point will be met during the heat of the day, and you'll have to drive through fog. It almost always happens either very late at night and continues very early into the morning. That's when the air at the Earth's surface has cooled to the dew point, and it can cause all kinds of traffic problems. But in normal conditions, that only happens much higher up in the atmosphere, which is why we see clouds there and not at the surface. So we only get fog when the air at the surface has cooled to the dew point because it's reached its saturation. So there are two types of fog that we'll discuss in this class. First, we have radiation fog, which is the type that we're more familiar with. That happens when the ground radiates heat away at night, and it causes the air above the ground to cool to the dew point on the Earth's surface. And of course, when that happens, we get a really thick layer of fog that can be very dangerous to drive through. And it makes sense. During the peak of the day, the Earth has been absorbing lots of heat from the sun, and to balance itself out at night, it will release that heat in the form of infrared radiation. And when that happens, sometimes it'll cause the air to cool to the dew point, and we'll get fog at the surface when that does happen. The second type of fog is called advection fog, and that happens when moist air moves over a cold surface, such as a lake, and lowers the temperature to the dew point. So say we have a lake and a very cold parcel of air moves over it, and it chills the lake water to the dew point, and fog will form just over the surface of the water. That's called advection fog. So next we'll talk about how clouds form. Cloud droplets form around condensation nuclei. So these are very, very tiny microscopic particles like dust, bacteria, smoke, pollen, pollution. And these small particles provide a surface that the water can bond itself to and condense. We talked about in the first unit how water has very special adhesive properties that it can bond both to itself but also to almost anything else, and that allows these cloud droplets to form around these particles. So if you get enough of these molecules together in the same place, that cloud will just keep growing and growing as those hydrogen molecules bond with the molecules around them. And eventually you'll have these clouds that are composed of millions and millions of these molecules bonded together. So rain is the type of precipitation that forms through the process of collision and coalescence in a relatively warm cloud. So as those water molecules keep bonding and bonding together, eventually it gets so big that the buoyancy force in the air can no longer overcome the force of gravity. And when that happens, the gravity will pull that rain droplet down to Earth. And it has to be in a relatively warm cloud because if it were any colder, it might freeze, and then it would no longer be rain. It would be a different form of precipitation like snow or sleet, which is kind of in between the two. Now, snow is the type of precipitation that forms in a very special process called the ice crystal process, or also called the Bergeron process, in very cold clouds, right? The clouds have to be freezing and well below freezing for the entire journey of that snow plate all the way from the cloud all the way to the Earth. If it's not frozen, then it's not truly snow. Snow has to be frozen all the way through. So the ice nuclei particles that snow forms from are very special because they're plate-like in shape, and they're always going to be hexagonal in structure because of the way that the hydrogen and the oxygen atoms bond together, and that molecular structure It's always going to form a hexagonal shape, always 6 sides. It might come in many, many different beautiful shapes when that crystal reaches the Earth, based on how it freezes and refreezes and breaks on its way down. But it'll always be 6-sided, no matter what it looks like. And with the exception of hail is kind of weird, all types of precipitation are produced either through the collision and coalescence process, like rain, or through the ice crystal process, like snow. The temperature profile of the atmosphere, how hot or cold the atmosphere is where that precipitation was formed, will determine which type of precipitation we have. So remember, snow, it has to be very cold and frozen all the way from when it leaves the cloud to when it hits the Earth, whereas rain is relatively warmer. It's still very, very cold when it forms in that cloud, but by the time it reaches the Earth, it's unfrozen and is well above the freezing level. So it's no longer snow. And then you have these weird types of kind of hybrid precipitation like sleet and freezing rain that were frozen when they left the cloud, but have unfrozen and sometimes refrozen before they hit the Earth. So cumulus clouds are relatively warm clouds. That makes sense, right? Because they're close to the surface. So they tend to produce rain and the other forms of precipitation that aren't frozen. Whereas snow tends to come from cirrus clouds, which are very high in the atmosphere, and they're very cold clouds. Cumulonimbus clouds are mixed clouds. So they're warmer at the bottom, and then as the air rises very quickly, it freezes at the top. So that'll spawn things like hail and other kind of nasty forms of precipitation. And finally, to wrap up chapter 4, we're going to talk about cloud forcings. So cloud albedo causes cooling or negative forcing. So as the sun sends its electromagnetic radiation to the Earth, the clouds that are in the atmosphere will actually reflect a lot of that back into Earth. So clouds are very light in color. They tend to be close to pure white, or at the least very light gray. So that gives them a very high albedo percentage. They don't absorb much radiation. They tend to reflect it. And that'll reflect any solar radiation that has bounced back from the Earth's surface back to the Earth. And it has a regulating effect that keeps the temperature stable and warms the Earth up. Now, cloud greenhouse forcing is different. That is an example of positive forcing, which actually changes the temperature rather than keeping it stable. So when the clouds in the ozone layer, there's too many of them, it'll actually trap the energy that would otherwise escape the Earth and reflect it back down to Earth. And as we add more and more of these clouds to the atmosphere, this greenhouse effect will increase and get worse and potentially cause the atmosphere to get too warm. So currently, overall, cloud feedbacks are causing net cooling worldwide. So not necessarily in every spot of the atmosphere, but over the entire Earth, these cloud feedbacks have an effect of net cooling in the atmosphere. The surface of the Earth would be cool if there were more stratus clouds, because it tends to have a more cooling effect than a warming effect. And that makes sense because stratus clouds are very low to the Earth's surface, so if there were more of those blanketing Earth, it would prevent a lot of solar radiation from ever reaching the Earth's surface. It would reflect it straight back into the atmosphere, and that temperature would never reach us, so it would cause a cooling effect. So it's a delicate balance with the clouds in the sky of trapping heat, but also allowing the right amount of heat to reach our surface. Because a lot of the other planets in our solar system are either way too hot or way too cold based on their distance from the sun, but also their cloud dynamics. Our atmosphere is just about perfect to support most forms of life. And that wraps up chapter 4. I'll continue with chapter 5 next.